Hi everyone, in this video we are going to take a look at how electrons occupy orbitals. Please read the VR textbook chapter 4.1 for more detail for this. And the homework associated with this lecture video is homework 4.1 that are Newton homework. Okay, so after you finish watching this video, please start working on your homework soon. Okay, so we are going to take a look at the quantum number that we learned from the previous lecture video. We're going to tie that back into the atomic structure by looking at more specifically the structure of the location of the electron in an atom. Okay, so I'm also going to tie this back with the Bohr's model that you also are familiar with as well, so that way you can get to see like what is the difference between quantum model versus the Bohr model. Okay, so this slide right here can be found on lecture manual page 53. Okay, so I'm going to take a look at the hydrogen atom first, which is the simplest atom because it contains only one electron and one proton. Okay, so the graph that we are going to plot is on the y-axis would be the energy. Okay, so this y right here would be energy. Okay, and what we are going to do is that the energy is going to go from lower to higher, right? So the arrow is indicate that energy is increasing. Okay, so pretty much you probably notice that this is n equal to 1. According to Bohr's model, we already see that n equal to 1 is the energy level that closest to the nucleus, right? So if you were drawing nucleus, okay, so this would be the location of nucleus right here, right? So the nucleus would be right here. Oops, sorry. Oops, let me erase this, sorry. Okay, so pretty much the n equal to 1 is the main energy level 1, right? The ground state that we learned earlier. But when we tie this back with the quantum number that we learned from the previous lecture video, we know that the main energy level or the shell n equal to 1 or principal quantum number 1, this value here is going to restrict the value of the angular momentum number L. Okay, so which means it's going to restrict this value right here, L. Okay, so when n equal to 1, the possible value of L can be ranging from 0 all the way to n minus 1, right? So if you do n minus 1, so number of n is equal to 1, minus 1 is equal to 0. Therefore, in this case, the only possible value for the angular momentum number L is going to be equal to 0. And the angular momentum number, which is L letter, is going to restrict the value of magnetic quantum number as well, which is ranging from positive value, including 0 and negative value. In this case, since the value of L equal to 0, therefore the M sub L would only be 0 in this case. Okay. So what does it mean exactly? Like as n equal to 1, if you write an orbital labeling for this, okay, when L equal to 0, this represents S orbital. Okay, so again, so this one right here, when L equal to 0, okay, so this represents S orbital. When L equal to 0, this contains, the 0 is one value, right? The number of value, how many value of M sub L is tell you about the number of orbitals, okay, within that subshell. Okay, so in this case, it tell you that the S subshell would contain only one orbital, okay, and the main energy level that this orbital resides would be in main energy level equal to 1. So if I write this as the orbital labeling, you are going to get 1s, right, where number 1 in front come from the value of n, right? So this one right here come from the value of n, and s is come from the value of L, right? And the reason why we have only one dash here, or like one line right here, or this space, one space here, is because we have only one orbital, because of we have only one value of M sub L. Okay, so that's where how we can interpret this. Okay, so pretty much all of these have the meaning, and these meaning are going to fall into the orbital labelings that you are going to use when you fill out electron in an atom later. Okay, so right now I'm just trying to like make you to understand this. Okay, so next Okay, so what I'm gonna take a look at is, so I'm gonna erase all of this for a second. Okay, so the next level would be n equal to 2. Okay, so when n equal to 2, of course, the value of L will ranging from, right? So we learned before from the previous lecture that when n equal to 2, L can range from 0 and 1, right? So that would be the maximum value. Therefore, in this case, you are going to end up with n L equal to 0 because that's one of the available value. And you are going to also involve with L equal to 1 as well because there are two values of it. Okay, so when L equal to 0, of course, M sub L equal to 0. If you want to translate these into orbital labels, it's going to equal to 2s, where 2 come from. Okay, so let me change the color real quick. Okay, so when 2 indicate that this orbital right here is precise in the main energy level 2, right? S, this is the orbital, is the subshell that is part of L equal to 0, right? And again, the reason why we have only one space for this is because there is only one value of M sub L when L equal to 0, right? That value is equal to 0. Okay. Now, if you take a look at when L equal to 1, when L equal to 1, M sub L is going to be determined or will be restricted by the value of L. The value of L will tell you about the value of M sub L. So if L equal to 1, then the M sub L would range from positive 1 to negative 1, including 0 as well. So therefore, in this case, there are 3 value of M sub L, right? So this 3 value of M sub L. Therefore, you are going to end up with 3 orbitals for this subshell. Okay, so that orbital, when L equal to 1, we know that when L equal to 1, we call this orbital p orbital. Therefore, you can label this as 2p, right? So each of these location right here, sorry, each of these value of M sub L tell you about the orientation of the orbitals, right? So along x-axis, y-axis, or z-axis, right? So which is indicated by this negative 1, 0, or 1. Most likely what you are going to see is that you can actually represent these 3 orbitals as 2p. And that is also correct as well because all of them are pretty much the same identical orbital level, it's just different orientation. Okay, so again, the reason why there are 3 orbital for 2p subshell because we have 3 value of M sub L. Okay. Now, if you do the same thing for n equal to 3, okay, so you are going to get when n equal to 3, the value of L would range from 0, 1. Let me, is this? Okay, so when n equal to 3, the value would range from 0, 1, and 2, right? Because it have to be up until n minus 1, right? So 3 minus 1 is equal to 2. So that means the maximum value of this would be 2. We already see L equal to 0. We already see L equal to 1. So that means when n equal to 3, you are going to reach when L equal to 2. Okay, so that's what we are going to include here. You probably notice that the p orbital, right? So p subshell will not start unless you have n equal to 2. N equal to 1 is always be 1s, right? N equal to 2, that's when the p subshell will start at, right? And then with the d orbital, it's actually start when n equal to 3. The reason for that is because it's going to match with L equal to 2. Okay, so again, so when L equal to 2, this is going to represent d orbitals. Okay, so let's take a look at that. Okay, so we already see this, right? So n equal to 3 can have L equal to 0. That's going to represent by orbital labeling as 3s. Okay, and when n equal to 3, L equal to 1, this is going to be p orbitals. Okay, so we talked about this before. 0 refer to s orbital, 1 is p, right? And again, because there are 3 orientation, therefore we will have 3 value of orbitals in the subshell 3p. Okay, so now when L equal to 0, in L equal to 2, then the value of M sub L would range from -2 all the way to +2, okay, including 0 as well. And there are 5 values of M sub L. Therefore, you are going to end up having 5 orbitals in this level that associate with this subshell. And we know that when L equal to 2, this is the d orbitals. Therefore, you are going to have d orbital throughout all of this. again, you can ignore this subscript here. Okay, this subscript just indicate that these are the different orientation of the orbitals. You can refer of this as 3D if you want to, because they all have the same energy. Okay, so all of these are 3D. The only thing that different is just the orientation around along the X, Y, and Z axis. Okay, so you probably noticed that the energy level of all of these are pretty much the same, right? So why is there a split then, right? So that why are we learning this then, since it looks similar to the Bohr's model that we learned earlier, right? If you're looking at it, right? So pretty much if you look at this, you are going to see that all this energy level is similar to what we learned in Bohr's model. Why do we have even why do we even have to talk about quantum theory then, right? So because if you think about it, Bohr model talk about the different level, right? So it's similar to if I would draw Bohr's model, it would be nucleus, right? So if this is nucleus, then n equal to 1, it would be that, right? And n equal to 2, okay, so you're gonna have 2s, and you're also gonna have 2p, right? So 3 of the 2p, oops, sorry. You're gonna have 3 of the 2p that are in the same energy level. Let me erase those. Okay, so this one is 2s, this one is 1, 2, 3, these are 2p, right? Since they are going to be in the same energy level anyway, so it's the same as what we draw in Bohr's model, right? When n equal to 2 and when n equal to 3. So why do we learn about this then? Is give us the same idea. So if you remember what I talked about earlier in the review session and also in the previous video, I mentioned that Bohr's model can be used to explain only the emission spectra for only hydrogen atoms. It's failed to explain emission spectra for other atoms. Okay, so again, Bohr's model work because it's matching with the quantum model. Okay, so the one that you see, okay, so the one that you see in blue right here. Okay, so I'm going to erase this subshell. Okay, so 1s to, oh sorry, n equal to 1, n equal to 2, and n equal to 3. So these are Bohr's model, right? These are Bohr's model. Okay, which is matching with the quantum model that highlight in yellow, right? So this yellow thing right here is the quantum model. Because quantum model give you what do you call a detail of the each energy level, right? That is tell you about each energy level is actually have sub energy level within each of those main energy level, right? So that's what it is tell us. So why do we care about this? So we are going to get into the multi-electron atoms, and you are going to see why Bohr's model cannot explain, but quantum model is able to explain better. Okay, because there will be the split in energy of some of these. Okay, so that's what we're going to take a look at next. Okay, but before we do that, okay, so what I want to make sure that you jot this down is that note again that these orbitals or sub energy level that within the main energy shell, they all have the same energy between 2s and 2p. This is applied to only hydrogen atom. Okay, so I'm talking about only hydrogen atom right now. Okay, so we call this term degenerate. When orbitals have the same energy level, we call this degenerate. So in this case, I can say that the 2s and the 2p subshells have the same energy, or they are degenerate. Okay. Same thing for 3s, 3p, and 3d as well. All these are degenerate, which means that they all have the same energy. Okay, so again, this only apply for hydrogen. This work only for hydrogen. Okay, so that's why Bohr's model is explain hydrogen so well, because they all have the same energy level. Okay, so now let's take a look at how can I use the quantum numbers in order to describe the structure of electron, right? So that we call that electron configuration. So there are two types of electron configuration. One is tell us about the location of electron in the orbitals, and the other one is show how the electron is arranged within orbitals. Okay, so one is called electron configuration. That is pretty much how how you are going to put how many electrons are going to each orbital. An orbital diagram is telling you how electron would rearrange within each of orbitals. So what do I mean by that? Okay, so let's start with hydrogen atom. Okay, so hydrogen atoms, if you look at the periodic table, you will see that hydrogen atom would contain 1 electron. Okay, so this one have 1 electron. So I'm gonna write right there. Okay, which is different from helium. Okay, so helium would contain 2 electrons because for neutral atoms, hydrogen has 1 proton, therefore it would have 1 electron. Same thing for helium as well. Helium has 2 protons and therefore it will have 2 electrons. Okay, so in order to write out electron configuration for hydrogen, okay, we are going to need to fill electron into the closest energy level that closest to the nucleus, because it has the strongest attraction force that is going to experience from the nucleus, right? So that means in this case, if you go back to, if you recall Bohr's model, we are going to fill in the energy equal to 1, okay? But this main energy level is not part of the quantum number. So that means in this case, I'm not going to write as n equal to 1, but I'm going to use the quantum number that we looked at earlier to fill this in. Okay, so if you go back to here, you will see that the first one is actually start from 1s, right? N equal to 1, the first orbital is 1s because that's the closest to the nucleus. So I'm going to do the same thing here. Okay, so I'm going to go back here. What I'm going to start at with going to be 1s. I'm going to fill out electron into 1s first because that's the closest energy subshell that closest to the nucleus. Okay, and because hydrogen has 1 electron, therefore the number of electrons would be shown on the top right corner as a subscript, right? So these would indicate 1 above s would indicate the number of electrons. Note that this s is actually lowercase s. Okay, so uppercase s means sulfur. This is lowercase s. I might have to like actually write that better so that way you don't get confused. So let me write that a little bit smaller. Okay, so 1s superscript 1. Okay, so again, if I have to write this out, n tell us that is n equal to 1, s tell us that this is going to be L equal to 0. Okay, and number 1 right here tell us the number of electron. Okay, so this is called electron configuration. Okay, so it tells us about the location of electron in orbitals. Okay, for orbital diagrams. Okay, so we are looking at 2 things right now. So first one that we're looking at electron configuration. Okay, the second one we're going to take a look at is called orbital diagrams. Okay, so this is going to be another one that we are going to look at, orbital diagrams. Okay, for orbital diagrams, you have to specify the how electron actually arrange in the orbital. Okay, so in order to do this is you are going to do the same thing, except we are going to have to write out the number of orbital for that subshell. Okay, 1s, because s is represent when L equal to 0, and when L equal to 0 is also restrict that the value of m sub L will also equal to 0 as well. And as I mentioned earlier, because we have only 1 value of m sub L, therefore the orbitals that we have, it would be just 1 orbital. Okay, so this would be 1 orbital. This is the orbital of 1s. Okay, and the number of electron that we see earlier now can be filled in here as the spinning of the electron. Okay, so again, the reason why I do only half arrow, because if you remember the electron, right? So m sub s, the value of m sub s from the previous lecture video, there are 2 possible values. One is positive 1/2, the other is negative 1/2. And these 2 values is going to indicate how electrons spin, right? So positive 1/2 would indicate spin up, negative 1/2 would indicate 1 down. So in this case, since we have only 1 electron, we are going to have only 1 half arrow that fill in an orbital. Okay, so if I label these would be called orbitals. Okay, and the top arrow right here would be the electron. Okay, so that's what it is give us. Okay, so the one on my left side, this is what we call electron configuration. The one on my right side, this is what we call orbital diagrams. Okay. Now, if you compare this with helium, okay, so I'm going to do helium. Because helium has 2 electrons, therefore, again, 1s, right, is contain 1 orbitals that can fill 2 electrons because there are 2 possible values of m sub s. Therefore, in this case, you are going to be able to fill out maximum of 2 electrons in the s orbital. Okay, so we can fill 2. So again, this number 2 refer as number of electron. Okay, if I write this as orbital diagram, what you are going to do is going to be the same thing, right? Because we have 1s, so 1s would be just 1 orbital. The reason for that, because when L equal to 0, there's only 1 value of m sub L, which is 0. Okay, so that 1 value translate into 1 orbitals. And because we have 2 electrons, therefore you are going to end up with 2 arrows. Remember, the value of m sub s have to be positive 1 or negative 1. Therefore, in this case, you are going to fill 1 electron up and the other down because of these 2 possible value of m sub s that allow electron have to be in the same orbital with different spin. Okay, because they are 2 different sides. And the main reason for that is because the different spin will allow them to be able to occupy in one space. If they have the same spin, they are going to most likely repel each other and they will not be occupied in that same space. So again, so in this case, it's indicate 2 electrons that have opposite spin, and then 1s would indicate the orbital that these 2 electrons reside in. All right, so we are going to get into more detail of how to do electron configuration and also orbital diagram later when we talk about the next lecture video 4.2, okay? But for now, I just want to give you some picture of like what are those quantum number is actually means, right? We see all the number, but what do they do, right? So what do they do? What is the significance of it? Like, what is the application? So here it is, right? So those quantum number are very crucial because it's actually going to help us to apply into how to fill those electrons into each of these orbitals. Okay, so the next thing that I'm going to look at is, before we look at only hydrogen, now we are going to take a look at multi-electron atoms, which mean these are the atoms that contain more than 1 electron, right? So we're gonna take a look at the energy level of each of those orbitals. Okay, so plot here is the same, similar to the previous one that I have earlier, right? So on the y-axis, we have the energy that's going up. So lower means it's closer to the nucleus, higher means it's away from the nucleus, okay? So again, so when n equal to 1, we already see that, right? So when n equal to 1, the orbital that resides in n equal to 1 is the subshell 1s that contain 1 orbital, okay? And when n equal to 2, we are going to observe the 2s and 2p. So similar to, if you go back to, so let me go back to here. So it's similar to what we already see, right? So you have 1s, 2s, 2p is come from all of this quantum number, right? When you have n equal to 3, you have 3s, 3p, and 3d, right? So if you have n equal to 4, you probably notice that you are going to end up with 4s, 4p, 4d, and 4. And, you know, like if there is like up to f, right? If L equal to 3, then you can do that as well. But in this case, before I do that, okay, so I would like to actually go back here real quick, okay? So 1s makes sense, but let's take a look at 2s and 2p real quick. Wait a second. For the hydrogen atom, these two between 2s and 2p, they have the same energy level. Remember, according to Bohr's model that is worked really well with hydrogen, right? The s n equal to 1 and sorry 1 n equal to 2, these are, so of these orbital within this, they all have the same energy level because they reside in the main energy level. But that is not true for multi-electrons. So that's why Bohr's model is only be able to explain the emission spectra for only hydrogen, but not other elements, because other elements have the split between 2s and 2p subshells. Okay, so that means in this case, these two right here still located in n equal to 2, but they have different energy level. Okay, so slightly different energy level, and n equal to 1, 1s will reside in n equal to 1. Okay, so that's what it means here. Okay, but again, the reason why this is different from Bohr's model, because the 2s and 2p right now for multi-electron atoms, they do not have the same energy level anymore. Okay. All right, so this is called splitting of the orbitals. Okay, the 2p, right, or the 2p will still have the same energy, but between s and p, that would be the splitting that will happen. This trend also apply when you are increasing the number of principal quantum number as well when n equal to 3 and 4. Okay, you start to see the splitting between of these, right? You start to see the splitting between S and P subshell and between P and D subshell. Same thing for these as well, right? So it's the same trend here. So this pattern of the orbital splitting is also known as Aufbau diagram. Okay, so we're going to talk about that later. Okay, so what I want you to look at more closely is why is there a split? Right, so that's what we're gonna take a look at. So why is there a split between 2s and 2p? Like, why is there a split right here, right? In comparison to like the hydrogen atom doesn't have a split, but why this one have a split? Okay, so this is when we are going to take a look at more than one electron now. Before we look at that, you need to understand the fundamental force first that hold electron within an atom. Okay, so the fundamental force that you will need to understand is the Coulomb's law. Okay, so the Coulomb's law is describe the electrostatic force between two charged particles. So the charged particle Q1, that's represent 1, right? That's the Q2 represent charged particle 2. Okay, so they both are going to interact with each other in a certain distance, or okay, the interaction for these can be described as the E, which is the energy. Okay, this energy right here is going to be directly proportional to the charge that they are interact, and also is going to be inversely proportional to the distance, which makes sense because the short, like the closer they are going to interact with each other better than the further they are. So that's why the interaction, right, is going to be inversely proportion to the distance, but directly proportion to the charge, right? The stronger the charge, they are going to be able to interact with each other stronger. So why do I talk about this? Well, because when we talk about interaction, we talk about two things. We either talk about repulsion or attraction, right? So repulsion is when you have these two to have the same charge, right? To have the same type of charges. But when we talk about attraction, these two have to be opposite charge, right? So for them to attract each other. So why do I talk about this? Well, if you think about Bohr's model earlier, right? So the reason why the energy of the electron here, right? The force of why it is more stable for this electron compared to the further away electron, because the force between the nucleus and the electron are stronger, right? Because these are close, these two electrons and the nucleus are closer. The one that further, right? The distance is further away, so the attraction force will not be as strong as the one that closer. If you want to think about this in terms of like relationship, that would be similar to that, right? Dating someone that is closer versus dating someone that is further away. So this would have a stronger interaction, right? So that's kind of like how I understand this. Okay, so why do I talk about this and how is that related to the 2s and 2p splitting? Okay, so you will need to understand first that we are looking at, when we are looking at atoms, when we look at only hydrogen atom, you have only one electron. So that means that one electron will not have any other interaction except only the attraction force between itself and the nucleus. However, this is not true anymore when you have more than one atom, one electron, right? For example, in this case, we have 3 electrons that orbit around the nucleus. Because this electron right here is not going to only experience the nucleus positive charge, but is also going to experience the repulsion from these 2 electrons that are closer to the nucleus as well, right? This effect is called shielding effect. Okay, so similar to if you think about when you go to the concert, right? When you are further away from the stage, you are not going to be able to clear the stage. So to see you are not going to be able to see the stage very clear. So similar to this electron as well, when you are further away from the nucleus, you are not going to be able to see the nucleus or experience the attractive force from nucleus very strongly compared to those electrons that are closer, right? Because this electron right here going to experience repulsion, also is not going to be able to see that very clear. Therefore, it's going to experience the actual net charge only about 1, right? Because you have 2 electrons blocking it, right? So it's similar to this picture right here. Because you are further away, it's just harder to see the artist like on the stage, right? So now think about this. What about if you are small enough and you can get through this crowd, right, to get closer to the front stage? Okay, so can you do that, right? So same thing for electron too. Yeah, so the orbitals can actually get penetrated closer to the nucleus, and this is called penetration effect, okay, where electron or the orbital can get closer, right? So that means in this case, it's similar to when you are like small enough that you can get through all of these people to get to the front of the stage to see or experience what is going on, right? So same thing here, right? So this electron is able to penetrate through it to get closer to the nucleus to avoid all this shielding effect from the electron, and also to avoid to get closer to the nucleus, right? So what is this penetration effect exactly? So this is where you are going to start to see the split. Okay, so this graph right here is plot between the radius. Okay, so this is measured in picometer, which is going to equal to 10 to negative 12 meter. Okay, so that's what it means. Okay, so R is the radius. Okay, so what does it mean is that the 0 is going to represent the one that closest to the nucleus, right? So the distance away from the nucleus equal to 0, right? So that means it's pretty much right here is the nucleus. The further away, right, 200, 400, 600, 800 picometer, those are the distance that we measure away from the nucleus, okay? And the y-axis, this is the probability of finding electron. You probably notice that 1s, right, have the highest ability to find electron, right? You can't even see the peak of it, and it's the closest to the nucleus, which makes sense. We already see when we draw the energy diagram, right? We see that n equal to 1, or when we have 1s, right? This is closer to the nucleus, right? And when we have 2s, the reason why that is the split, because normally in Bohr's model for hydrogen atom, you are going to have n equal to 2 like this, but because we don't have only 1 electron anymore, we have several electrons for other atom that is not hydrogen. Therefore, in this case, the 2s and 2p is going to start to split, right? So in this case, your n equal to 2 will look like this, right? So you're gonna have 2s and 2p that's split. And the reason why they split, because if you're looking at this, right, the probability of finding electron between 2s and 2p, okay, so the red one is the showing the probability of finding electron, okay, so it seems like 2s is away from the nucleus and 2p is closer, but that's not true, because if you're looking at this small little bump right here, this small little bump right here is actually closer, right, the peak of it, right, so this peak right here is actually closer to the nucleus, okay, than the peak of the 2p, right? So these little bump right here that can get closer to the nucleus, this is what we call penetration effect. Okay, so it's small enough that it can actually get closer to the nucleus, as I mentioned earlier, right? With the, you know, like when you go see the artist, right, at the concert and things like that, right? So small little bump right here will be able to penetrate, get closer to the nucleus. Therefore, in this case, you are going to end up with the 2s to have lower energy than the 2p, because 2s is closer to the nucleus, it's experience a stronger attraction force, therefore they are more stable, okay? So 2p is a little bit further away, therefore in this case it's going to be it's going to have a higher energy state. which means that it's going to be less stable for that. Okay. All right, so let's take a look at the summary of this if you want to write this down. So pretty much this little bump right here is the probability of finding electron that close to the nucleus, right? So that means the reason why that is the split, because the 2s subshell has greater penetration and is therefore going to experience more nuclear charge and less shielding than 2p, right? Because get closer to the nucleus, therefore it's going to experience a lot more of the charge from the nucleus. Okay, so which make it to be more stable. Okay, so this is another one that you can actually write this down as well, that the penetration effect of the 2s orbital allows the 2s to get closer to nucleus, therefore the energy of 2s is lower. So exactly the same way that I explained earlier, but just different wording. All right, is this true for others like level, right? So right now we talk about n equal to 2, right? So the next thing we're going to take a look at is n equal to 3. Okay, so when we increase n equal to 3, this graph is the same as the previous graph that I mentioned earlier. You are plot between the distance from the nucleus. This far left represent that this is closest to the nucleus. Right? This is closest to the nucleus, and the far right would be further away from the nucleus. Okay, and this is the probability of finding electron. You probably noticed that the 3s has this tiny little bump right here that can penetrate to get closer to the nucleus. Again, because 3s has the penetration effect, right, stronger than the 3p. Therefore, 3s probably going to be able to get closest, and also is going to have the lowest energy compared to 3p and also 3d as well. Okay, so 3s is this one right here, 3p is this one, and 3d is this color. Okay, so if I need to arrange the energy for each of these orbitals, note that I'm comparing with the same n value. Okay, so what I'm doing is I'm comparing with the same n value, which means you are comparing with the same n, right? So this is when n equal to 3. Okay, so we will see that when you are comparing with the same principal quantum number, you're gonna see that the energy of the s orbital would be lower than p, and it would be lower than d, and of course the energy of the f orbital would be the highest when you are comparing with the same principal quantum number. Okay, so that means in this case, when you have let's say 4s versus 4p versus 4d versus 4f, you are going to see that the 4s would have the lowest energy compared to the 4f, right? The 4s would have the highest energy, which means it's going to be not very stable. So the electron would most likely to reside in the 4s first before it can fill in the 4f. Okay, so that's what it means here. All right, so now we're gonna take a look at, since we already see why there is the split, right? So if you're looking at this, it's exactly what I mentioned earlier. Because with the same principal quantum number, right? So this is the same principal quantum number. This is the same principal quantum number, n equal to 2. This is when n equal to 1, right? So 1s is the subshell that reside into the main energy shell. Okay, so these are the subshells that reside in the main energy shells. Same thing for 3D as well, right? This is going to represent n equal to 3, right? So that means all of these 3 subshells right here would reside in the principal quantum number equal to 3. That's what it means here. Okay, so if you look at these, you will see that of those are the split that I mentioned earlier, right? So of these are the split that I mentioned earlier. The reason for that is because the s orbital have a greater penetration effect than the p orbital, and p orbital has a greater penetration effect than d orbitals, right? This is when we compare with the same principal quantum number, right? So when we compare 2p and 2s versus 3s, 3p, 3, or like 4s, 4p, and 4d, you will see that sp, ds would have the lowest energy because it's able to get closest to the nucleus. Okay, so when you are going to fill in the electron in an atom. Okay, so this is going to help us to understand next lecture video better. Okay, so you are going to use the Aufbau principle to fill in electron. Aufbau principle state that when you are filling electron, the electron must be added to the lowest energy orbital available first, which means if you are going to add electron, you need to add into this level first. Once it filled, then you're going to the next. Once it filled, you are going to the next, right? And once it filled, you're gonna go to the next and next and next, and you see the picture of that. Okay, so this principle right here is called Aufbau principle. Okay, so you're gonna fill into the lowest energy level first. Okay, so this type of electron configuration that we are going to see in the next lecture is called ground state, because ground state means it's the most stable state. Okay, so it have not been radiated or activated by any photon yet. Is the is in the stable state. That's what it means. Okay, so these order right here, if some of you who taken high school chemistry before, you might see some of this diagram right here that start from 1s, 2s, 3s, 4s, and then followed by 2p, 3p, 4p, 3d, 4d, and then 4f. The reason why, again, we don't have 1p because this one is not exist, right? It's invalid. You already see that when we talk about n equal to 1, the only one value for L would be 0. This represents S. Therefore, in this case, you cannot have p orbitals. That's why it starts right there. Okay. So same thing for when n equal to 2 as well. When n equal to 2, you have L equal to 0, which is represent S. You have L equal to 1, which is represent P. And it stopped right there. So therefore, you will not see the 3D in the two, sorry, you will not see the orbitals in two when n equal to 2. Okay, so it's come from that. Okay, so again, so all of these, the reason why it's missing some of the F, some of the D, or some of the P, it's just because of the restriction of the quantum number that we talked about earlier. Okay, so it's come from those restriction. Okay, so let me do one more with the 3D, right? So the reason why for, F start with n equal to 4, because if you think about this, when you have n equal to 3, right? This level is n equal to 3, you are going to have L equal to 0, which represent 3s, L equal to 1, which represent 3p, and L equal to 2, which represent 3d. And you cannot have more than 2 for the L value, therefore it's going to stop at 3d. Okay, so it's come from what we learned earlier about the restriction of the quantum number. Okay, so if you learned from high school the way that you can fill this energy diagram, sorry, electron configuration diagram would be, you are going to start from 1s followed by 2s, right? After you finish, you follow by 2p, then you follow by 3s, you follow by 3p, and you follow by 4s, and so on, right? So it's going to be similar to what we have here. Okay. But I don't use this diagram often because in the next video, you are going to learn how to fill out electron configuration by using the periodic table. And that's what I highly recommend you to use the most, because it's the most convenient. It doesn't require the memorization of this order. Okay. So pretty much what you need to know for this slide is that you just need to know that when you fill electron, is have to go to the lowest energy first. That's what we are, that's what, that's the take home message of this. And because each of these orbitals, right, can have two value of m sub L, oh, sorry, m sub S. We talked about this before, that the m sub S value that fill in each of these, there are two possible value, which is positive 1/2 and negative 1/2. Therefore, if you're looking at this, that means each of these electron, whether it's spin up, right, or spin down, it can fill into each of these orbitals. Therefore, you will need to also know the number maximum of electron that can fill in each of these as well. Okay, so for example, 1s, you are able to fill in only two electrons because you have only one orbitals that can accommodate either positive 1/2 or negative 1/2. Same thing for 2s as well. So that means all the s can have only 2 electrons. But if you are filling P, you will see that you can fill 1, 2, 3, 4, 5, 6, right? You fill 6 because each of those orbitals can accommodate 2 electrons, spin down, spin up. Same thing for 3p as well. You can either have spin up or spin down, right? And you are going to fill total of 6 electron total, right? So if you count this, there are total of 6 electron. For S, there are total only 2. And D, because the orbital, D subshell contain 5 orbitals, so each of those orbitals can contain 2 electrons, therefore total would be 10. So this is where each of those number of electrons can be filled in each of those come from. So now if you want to look at F, right? So because F contain 7 values of M sub L. Okay, so let me actually write that real quick. So if you think about F orbitals real quick. Okay, so let me change the color. Okay, so when we talk about F orbitals, so when we talk about F, it's going to restrict the value of L to be N equal, L equal to 3, right? So in this case, if you write the M sub L value, you are going to get from -3, -2, -1, 0, 1, 2, and 3. If you count off these, you will see that there are 7 values of this. Okay, so 7 values. 7 values. So that means you are going to end up with 7 orbitals. So 1, 2, 3, 4, 5, 6, 7, right? So if you fill 2 electrons for each of those, you are going to get total of 14. That's where the 14 come from. Okay, so pretty much what you will need to understand is that you will need to know this maximum of electron that can fill in each subshell. Okay, so this is going to be crucial for our next lesson, for the next lecture video. Okay, all right. So the second rules that you will also need to know when you fill in electron is the Pauli exclusion principle. Pauli exclusion principle states that no 2 electrons in an atom can have the same set of 4 quantum numbers, which means they will not be able to have all the same set of NL, M sub L, and M sub S. Okay, so the reason for that is because there are only 2 possible values of M sub S. Okay, so that means the orbital can hold only 2 electrons. Okay, so what do we mean by that? Okay, so let's take a look at a set of quantum number. Okay, so for A, okay, so if you will write this set of quantum number, okay, N equal to 2, you can write this set as 2, right? And when L equal to 1, okay, so L equal to 1, this represents P orbital. So that means in this case, it's actually represent 2p. And for 2p, because L equal to 0, L equal to 1, you are going to end up with 3 possible values of M sub L. Okay, so it would be M sub L -1, 0, or +1, right? So these are 3 orbitals that come from the 3 different values of M sub L. But in this case, you will see that this orbital right here, M sub L -1, contain the electron that is +1/2. Therefore, if I label this one right here as M sub L equal to -1, I can write that this is going to be my spin that is going to pretty much imply that it's equal to this electron right here of M sub S, +1/2. And the other orbital, which is the same thing, right? M sub L equal to -1 is the same orbital. So that means I'm going to fill into the same orbital, but different spin. Okay, so that means in this case, I'm going to be able to fill that into the different spin. That's what it means. And when M sub L equal to 0, this is going to be that it's going to go to the different orbitals now and with the positive spin. Okay, so that means this set of quantum number A would be valid because no electron resides in the same orbital that have the same 4 quantum number, right? Because this is almost the same, but the last one is not the same, so that's still allowed, right? Because the last one have to be what do you call, like the opposite spin as the one that you feel earlier. Okay, so now what about B? Okay, so is B okay? Okay, so same thing. I'm still talking about the same orbitals or the same subshell and same orbital as well, because we talk about N equal to 2 and L equal to 1. So for B, we also talk about the same thing. We talk about 2p. Okay, 2p contain 3 orbitals. Okay, so we know that 1 for m sub l would be like this. Let's say like we're going to assign this as m sub l equal to -1. We have the positive 1/2 for the electron to fill. Okay, so that's spin up. This one right here is different orbitals because this is different orientation, right? So I'm going to fill out right here. This is also positive 1/2 too. The last one is the last m sub l, so that means it's going to be this one right here is also positive 1/2 too. So this is also allowed because each of these electrons are in different orbitals, so that means the set of quantum number for all of these would be different, so that would be allowed still. Now what about C? Okay, so if I look at C, I'm still talking about the same thing 2p because the value of n and the value of l still the same, so 1, 2, 3. Okay. However, if you're looking at m sub l1 right here, this one is equal to, let's say that it's going to be this one, right? So we already say like -1, 0, and 1. If m sub l equal to 1, I'm going to write right here, and it's going to be spin up, right? Because positive 1/2. So I'm going to write that as spin up. Okay. And the second one is m sub l equal to 0, which is going to relate it to this one right here in the middle. Okay. So this is also positive 1/2 too. So I'm going to write it down. The last one is m sub l equal to 1 as well. So I'm going to fill out to the last one that we just did earlier. And we are going to fill positive 1/2 also. But if you do this, you will see that this one is invalid because the last 2 electrons that fill into that orbitals have the same spin. They are going to repel each other, which means that these 2 electrons are going to have the same set of quantum number, which is going to violate Pauli exclusion because these 2 have identical set of quantum number, right? Both n and l value, right? Also both m sub l and m sub s value as well, right? So this is an example of Pauli's exclusion principle violation. Okay, so pretty much you just need to make sure that all of them have to have different set of quantum number. Okay. All right, so the next thing we are going to take a look at is the last one is called Hund's rule. Okay, so Hund's rule states that if you are going to fill electron, you need to fill them singly with the same parallel spin first. You are going to fill them half filled, okay? And after you fill them half filled with the same parallel spin, then you are going to start pairing them, okay, with the opposite spin. What do I mean by that? Okay, so for example, I'm going to take a look at 2p that we did earlier. Okay, so for example, in this case, let's see. So 2p has 3 orbitals. Let's say if you have 4 electrons, what you are going to do with these 4 electrons that you are going to fill in, you will need to fill in orbitals singly with the same parallel first, which means that you are going to fill this with spin up 1, 2, 3. You're not going to pair them yet. You're gonna fill them singly first in each orbital with the same parallel spin. And then the last one, since you already spent only 3 electrons, the last electron then will have to pair, will start to pair up, right? If you have 5 electrons, then it's going to start to pair up, and then you stop right there. But you have to fill them singly with the same parallel first before you start to pair them, okay? If you have only 3 electrons, then what you are going to end up with would be, this would be the answer right here for 3 electrons, because you have to fill them with singly parallel first. You cannot pair them right away, okay? Okay, so that's what Hund's rule means, okay? So example 4 here is going to actually give you an example of all the violation that violate all these 3 rules that we are going to use in the future. Okay, so let's take a look at which one is exactly that violate Hund's rule. Okay, so let's take a look at A. Is A correct? Okay, what A is violate? The A set of orbital diagram is that it's violate Aufbau because you actually fill in 1s, and instead of fill in 2s, it jumped to 2p first, which is not allowed because you have to fill in the lowest energy level first before you go to the highest. Okay, so this is an example of the violation of Aufbau's rule. Okay, for B, okay, remember we talked about there should be no 2 electrons that have the same set of quantum number. So clearly right here, these two electrons would have the same set of quantum number because they both are located into the same orbitals with the same spin, right? So this is would be an example of Pauli's violation. Okay. Now what about C? Okay, so C, we have one S and fill in two S and fill in two P. So that's good. Let's follow Aufbau principle. And what about, does it violate Pauli's exclusion principle? The answer is no, because all of these have different quantum numbers. So that's good. But it's violate Hund's rule. The reason for that is because you need to fill them with in the singly orbital with the same parallel first. So this is the one that is not in the same parallel. Okay, so this is the one that is not in the same parallel. So you can actually have to flip that. If you flip this, you should be, so the diagram should be correct. Okay, so in this case, since it's in the opposite spin, so this is the incorrect one. Okay. Now D is the choice that also violate Hund's rule as well, because you will need to fill them singly with the same parallel first. You can't pair them first, right? So this would violate Hund's rule. Okay, so again, of this rule, I'm going to refer this back again in the next lecture video. So I would like you to actually understand what are these rules. Okay, so if you not understand, just make sure that you actually write out the small definition for yourself to recall when I actually talk about this in the next video. So that way you know exactly what I'm talking about. Okay, so pretty much, again, we're going to use these three rules to help us write our electron configuration for the element in the periodic table. Okay, so after this lecture, you should be able to start working on homework now for the review quantum numbers and also shape of orbitals as well. And there are also more practice for you to do Pauli's exclusion principle and also the Aufbau principle as well. Okay. If you have any questions or need help for chemistry, please note that I have office hour posted on Moodle, and also we have Sign Help Desk drop-in tutor that you can actually access the Zoom link through Moodle as well. And we also have the one-on-one tutor through the tutoring center that you can make by appointment as well. Okay, so those are the three resources that you can use.